transfer functions is what we covered last class. And in transfer functions, it's this ratio of polynomials. It's the output as a function of s over the input as a function of s. To convert to an S-plane representation, you plot the zeros, the roots of the numerator, and you plot poles, which are the roots of the denominator of h of s. So as a quick example, if your h of s look like s over s plus 1, then that has a 0 at s equals 0, right? If you put s equals 0 into this equation, it'll be 0, and it has a pole at s equals minus 1. And so if you were to plot that, where this is the real part and this is the imaginary part, you'd have a 0 here, and you'd have a pole out here at negative 1. And just appreciate that for a moment, that this h of s represents a circuit. You've converted a real-world circuit into a ratio of polynomials. You've converted that ratio of polynomials into 2 points on a complex plane. And those are all equivalent representations of this same circuit. And this is a unique representation of the circuit. There are no other polynomials that look like that aren't, easily reducible by just dividing top and bottom by the same number. Same thing down here. This is a unique representation of that circuit within a scaling factor. Because obviously, if you multiply this top number by 3, it's got the same S-plane. But except for within that ratio of a constant scaling factor, this is a unique representation of your h of s, and therefore within a scaling factor, a unique representation of your circuit. How to convert it to a differential equation? That's when you cross multiply. So as an example, the same h of s, that's s over s plus 1. Remember, that's your output. I'm going to abbreviate output because it takes too long to write. I'm going to abbreviate that as my y of s over my x of s, capitals because we're in the frequency domain. So if we cross multiply, we end up getting s x of s equals s plus 1 y of s. And now, since s's are like derivatives in the time domain, that would be x prime of t equals y prime of t plus y of t after you multiply that out. And then last, we can get our impulse response really easily from our transfer function. Our impulse response is the response of the circuit to an impulse. So you could try to figure out what is its convolution with, but it's even easier than that, because h of s Laplace transforms to h of t, which should be just a little bit mind-blowing, that your h of s, which is again this ratio of polynomials, which is somehow intimately linked with differential equations, if you just inverse transform, you go from a differential equation representation into a time domain representation that is unique for what happens when you hit it with a hammer.
Sir, I'm getting a bit lost in all the different ways of converting and all that. If we have time in the class, would you be able to take a practical example of like a circuit and walk through like how to convert to each one?
Well, so that's
and explaining what they mean.
So Joe, that's exactly what I've done so far here. The only thing that I haven't done is gone from a circuit to your h of s. But we just did an example of that problem just seconds ago. Over here, we took a circuit and we converted it to this h of s. So there's that first part of what you want. And now here's the second part of what you want. Given an h of s, now I'm going to walk you through and convert it through each step from an h of s to a differential equation to a, looks like I put my line here in a slightly wrong spot, to a S-plane representation, a differential equation, and an impulse response. So I'm doing exactly that right now. And let's finish that example up. And you're right to get confused. There's a lot of different equivalent representations, which is why I'm taking time out with this particular class to cover it. There is a lot to take. Our h of t is just that inverse Laplace of h of s. So let's do it again with the same exact problem. We have our h of s is equal to s over s plus 1. Hey, is that proper? Preston?
I'm sorry, what?
Is this, so we're continuing on our work to convert between all these different equivalent representations. And we're down to finding the impulse response. So these are our, S-plane, differential equation, impulse. For our impulse response, we want to just it's just the inverse transform of our transfer function. There's a lot of ways we could find the impulse response, right? I mean, we could have taken it from our differential equation and solved it for an impulse in. We could have fed an impulse in the frequency domain, multiplied it by our system transfer function, and then inverse transformed the result. But the fastest way to find an impulse, h of t, is just to inverse transform h of s. And for this particular example, I've been working through this one example for all the problems, just like Joe asked. H of s, we want to take its inverse transform to find its h of t. How do we take its inverse transform? What's the inverse transform of this? Would we want to say, well, that's equal to something over s plus 1 and then use our cover-up method? No, because it's not a proper fraction. And that's why that method won't work. Instead, what do you have to do for a proper fraction, Preston?
I mean, don't you have to convert it to E? That's the inverse Laplace transform is.
That's our goal, to take the inverse Laplace transform. And how do we do that? We've got this transfer function. We want to take the inverse Laplace transform. How do we take an inverse Laplace transform of that? Do we use the cover-up method?
No, I don't believe so.
Not at least initially. We got to firstly make sure it's a proper fraction. Is it a proper fraction?
Yes, I think so. I'm not.
No. So a proper fraction says that the biggest power of s in the denominator is bigger than the biggest power of s in the numerator. But here the biggest power of s is 1 in both. It's s raised to the 1 power in the numerator. It's s raised to 1 power in the denominator. So it's not a proper fraction. So we're going to have to do something to get it in a proper fraction before we can take its inverse Laplace transform. It's all right. It's been a while since you've covered that inverse Laplace transform, but that's one of our first steps. Get it in the right format and get it in the correct format, and then make it proper. How do you convert this into a proper fraction? And Preston, you're still on. There's one technique. Anyone want to help him?
Polynomial division?
Yeah, just do a division. So it's s plus 1 into s. And that goes 1 time, so that gives us s plus 1. And then we subtract, we have minus 1 left over. And so that whole thing is equal to this. So this, an equivalent representation is this. And Preston, now back to you. Is this a proper fraction?
Yes.
Yes, because the biggest power in the s in the numerator is 0, and that's less than the biggest power of s in the denominator. So now you can inverse transform that. And what do you get from that, Phil? What's the inverse transform of 1?
Shoot, the inverse transfer to 1, isn't that the impulse function?
That's it. And then how about this guy?
You minus e to the negative t.
That's it, u of t. So we've covered So that's the impulse response of this function. So once again, once you know it's h of s, you can find, we've just covered finding its difference equation, going from the circuit to the h of s. That was our very first problem on the other board. H of t and s-plane. So these are all the ways we can describe how to convert it back and forth. There's a couple of neat things about the s-plane I want to talk about right now before we hit state space. But just before I do, any questions about this whole middle side of the screen, about those 5 equivalent ways to represent what a system is? And realize that this is more than just a circuit. While I've drawn a circuit up here as its entrance point, if you have any kind of system, like that mechanical system we did before, we start off with a difference equation, and then we could do any of these things. If you wanted to analyze portions of how the stock market works, you could come up with a block diagram description, and then from that block diagram, you could design a difference equation that described it. That's, if you're interested in that, that's in DSP, EE 341.